Alright, the mass of my calorimetry can is 36.94 grams. I've got exactly 100.0 milliliters of water. Water should have a density of 1 gram per milliliter, but let's pour it in and find out what our combined mass would be. Alright, so our can and the water for part 1 is 135.90 grams. The initial mass of our candle is 31.92 grams, and we did not use an index card. Instead, I built a little home inside of this aluminum foil. The idea is that we want to direct as much of the heat that's released from the combustion of the candle to the can and really the water inside of the can. And so that's the goal of this little aluminum foil housing that we built here. Alright, so I've got the calorimetry set up. There is an initial temperature of 21.5 degrees Celsius. That is for the water. The temperature probe has been sitting in the water inside of the can. The goal of calorimetry is to track heat flow. And so we're going to track the heat coming from this candle as it's burning, going into the water, and based on the changes of the water, we'll actually be able to calculate Q, which is heat. And the assumption that we're making is that all of the heat from the candle is going into the water in the can. Obviously, that's not going to be completely true. This is not super sophisticated calorimetry. There are much more sophisticated lab setups with calorimetry. This is just basic tracking heat flow, and there's obviously going to be a lot of error involved as we're going to lose heat to the surroundings instead of just going into the water. But that's the assumption we're going to make, is that the heat from the candle is all going into the water in the can. Alright, so I'm going to light my candle and then put it underneath our can here, and then I will probably lower this just to get it right up next to the candle. And then we're going to track temperature. We're going to wait for the water temperature to go up about, give it a little enclosure there. We'll wait for it to go up to about 40 degrees Celsius, and then we will measure the mass of our candle as well, so we can figure out, based on each gram of candle burn, how much heat is being released. That's essentially the energy density. Okay, so I'm just going to let this run. I will probably come periodically and give it a little stir just to make sure that we're distributing the thermal energy inside of the water in the can, but otherwise we're just going to kind of track it over time and wait for the temperature. The temperature is going up because energy is currently going, there is heat flowing from the candle into the water. Alright, so it looks like we're over 40. I'm just going to give it one final stir, and I will blow out my candle. And we can record the final temperature, T2. Looks like about 41.6 degrees Celsius. And then we shouldn't really have to measure the final mass of the water because that wouldn't really have changed, it didn't vaporize. But we do want to take the final mass of our candle. So then we can figure out how much wax burned, how much paraffin, and then we can actually figure out the energy density of the paraffin. So it looks like final mass of 31.27 grams for our paraffin. And next up we will do another calorimetry trial, and we're going to combust ethanol instead, and then we can compare the energy density of the two fuels. Fuel number one was paraffin wax, which is a hydrocarbon.